lunchtime seminar of the year. Thank you for coming to the first Quantum Science Centre lunch seminar of the year. So today we have Andy Albrecht from UC Davis. He says he doesn't care much for introductions, which is good because I'm terrible at them. His background is in cosmology. He spent some time at Fermilab before moving to Imperial. Was a key player in early theories of inflation, and these days, as always, enjoyed a bit of quantum foundations, quantum information theory. It's a wide range of interests, and I think the talk today is going to really sit at the intersection of all of these. So thanks, Andy, and I'm going to say on your behalf, because I think you're probably going to say it too, please feel free to interrupt with questions and discussion. I think this is a talk that lends itself to that.
Yes, and that's my style anyway, is I love questions. Ask as many as you want, and I'm pretty good at managing the time so we end at a reasonable time. And I much rather sort of navigate my material, allowing space for whatever questions show up, rather than stick to some rigid plan. So that's my style. So this is a topic that almost everyone who hears about it thinks it's trivial. About half the people think it's trivially right, half think it's trivially wrong. And so we'll see what you think. But it makes for a lot of fun. I want to start, so this draws on many different topics from physics, and I'm going to explain every piece of it in due course, but I'm going to start by just talking about my journey into the subject, which will just include some buzzwords, which I'll explain later. So just tolerate a few minute or two of sort of chatter about the story. So something like 30 years ago now, I was chugging along doing, oh no, I forgot what my next slide is. Okay, so I want to guide you. My first few slides is actually to guide you through the material and orient you a little bit. So if you've thought about the multiverse, eternal inflation, cosmological measure problems, well, if that's true, you're totally prepared to appreciate the context of this talk. If not, don't worry, I'll introduce enough of these concepts at a totally introductory level. And if that's still confusing, you can actually ignore the cosmology, because I'm going to say some things that a lot of people find provocative, just about everyday physics, laboratory physics. So you can just orient yourself here and get a lot of stuff, and have lots of questions for me even there. So don't feel concerned if this larger world of cosmology isn't your thing, because it doesn't have to be how you think about this topic. And in fact, what I'm actually doing is based on undergraduate physics only, although put together in a way people tend to find surprising. Okay, so now I talk about my history with the topic. So about 30 years ago, I was working on some project, and it occurred to me that it made sense that all the times we use probability in everyday life and in physics, such as a coin toss with a card and so on, are actually quantum probabilities. Not with quantum coherence and all, but with Born rule probabilities coming up from microscopic levels. And which is something I'm going to explain in this talk. So it occurred to me, and I thought, okay, so what? I've got interesting projects to do, I'll go work on them. And I put that topic on the back burner. And I also assumed somewhere in the journals of physics, there were people who had worked on that and worked it out. So I didn't seem like a research topic for me, it just seemed like an interesting thought. Then in about 2009, Don Page comes along and writes a paper saying, when you think about the multiverse, when you think about a universe where there could be many copies of our universe, there are key questions in such a picture, which quantum probabilities cannot address. You cannot, even if you perfectly knew the wave function for the whole multiverse, you couldn't come up with quantum probabilities to address key questions. And I'll show you exactly what I mean about that in a little bit. But he said, so what? We just use classical probabilities. So if we can't have a quantum probability, let's use a classical. He sort of took the point of view, classical probabilities are everywhere around us, and so we can certainly use them here. And then, so I took this topic off the back burner and said, hey, hang on, there's no such thing as separate classical probabilities. They're all really quantum. So what are you talking about there? And I slowly learned that this belief I had was not commonly held. And in fact, other people like Jim Hartle, Mark Trinity, Anthony Aguirre, and Max Tegmark joined in this discussion of all the ways you could use classical probabilities when quantum probabilities were not available. And I felt this conflict seemed like a deeper problem for the multiverse than some of the other problems people worry about. And potentially even for more tame cosmologies that don't have the infinities of the multiverse. But I couldn't, what I wanted to do was find all this literature I imagined existed talking about this subject, but I couldn't find anything. I called up people who should know, and it just didn't get anywhere. And I was sure that literature was there, but I reached a point where I thought the best way to uncover that literature was to write a paper, and at some point somebody would say, "Oh, you should have cited. Don't you know these famous papers?" But it still hasn't happened. So the paper came out 10 years ago now, and so now I'm pretty convinced it's original. Okay, so I'll say a couple more things before I really get started. In the end, this is fundamentally about giving ourselves permission to dismiss certain probability questions, the non-quantum ones, as ill-posed, rather than rushing to import classical ideas. Say, oh, there's no answer to that question. Maybe we should just accept that. And perhaps this type of discipline actually resolves. So instead of saying this is a deep problem, maybe this is a deep solution to a deep problem, where we can sort of cross out our worries and just say, no, just ignore, if you ignore certain questions that don't have quantum answers, maybe we can do a better job of making sense of the multiverse. Or not. So I'm not sure about that. And then, just this year, I've been having a rash of conversations about different interpretations of quantum mechanics. And I'm sort of comfortably a many worlds person, although I try to give this talk in a way that doesn't matter what your favorite interpretation is. And I tend to not enjoy debates about interpretations of quantum mechanics, but I've noticed there's interesting people in my life who've drawn me back into these discussions. And this topic, and I realize this topic is actually very relevant to a particular piece of those conversations about interpretations. So, and I'll point that out later in the talk as well. So that's kind of the context for this talk. Now here's the outline. So I'm going to talk about what I mean about quantum versus non-quantum probabilities. First of all, in a toy model, and then in a cartoon of the multiverse. So you don't have to study the multiverse, I just give you a cartoon of that. And it may be actually that the problem lies with the cartoon rather than any realistic model. I'll comment on that. Then I'm going to put that aside and talk about everyday probabilities and why I think they're quantum, like flipping a coin and so on. And then there's some lessons learned, and sort of depending on how much dialogue we have, how much time we take up with our conversations and questions, I'll hopefully at least get to some points about counting arguments. We're used to using counting arguments to relate to probabilities. So you can count, how many of this, how many of that turns into what probability you have for getting this or that. And I'm going to argue you've got to be careful about that. And then we'll see, there's lots of other implications, and I don't know how far I'll get with that, but there's plenty to talk about if we have the time. Okay, so digging in. So I'm going to tell you just a little bit about the multiverse, and I'm going to start by saying cosmic inflation theory is this, at this point, is a fantastic workhorse in the field of cosmology. You have people taking absolutely amazing data sets. This is data describing maps of the microwave sky, looking back almost 14 billion years in time to the very beginnings of the universe. And that's mapped out by microwave background data. This is from the Planck satellite. And you can take this amazing data with these tiny error bars, and then you can shoot a theory curve through it. And if that isn't what we love to do in physics, I don't know what is. You have data, you have a theory, you can go through it. And in that role, inflation has just done marvelously well. Now I'm going to give you a cartoon of what's happening in the machinery of inflation. You have a scalar field rolling down potential, and there's a certain period of that rolling process where the observable universe is generated. That's all I'm going to say. Those of you who know the theory know what I'm talking about, but otherwise, I'm just going to say there's this period, this physical degree of freedom, it's moving in the potential, and during a certain period of that rolling, all the observable features in the universe are generated. And then you could ask, what happens before? So if this is what was happening, and it generates all these beautiful curves that can fit the data, what was happening before? And it turns out this rolling is actually pretty classical. Not as classical as a basketball, but it's pretty classical. 1 part in 100,000 classical. And so it's very, very natural to say, well, if this was happening, then a little bit before that, it was just a little further up the potential. So it's a very comfortable extrapolation to do. And then you can keep doing that extrapolation. But eventually, you actually get to the point where the behavior is very quantum. And in some simple-minded cartoon of this, you say it's just as likely to quantum fluctuate up as down. And then that turns into a whole different picture. So the point, the feature, one of the features that's very relevant for the cosmology story is that when this field is up the potential, the universe is expanding exponentially. And eventually, as it gets close to the bottom, the exponential expansion stops and you get something more like the realistic, well, now the universe is expanding exponentially again, but for most of the history of the universe, at least by some measures, it's not been expanding exponentially. So there's a transition at some point. But the high level of quantum fluctuations mixed with the exponential expansion actually leads to a picture where most of the universe is exponentially expanding forever. And only little regions fluctuate down and start rolling down and make universes that could be ours. And they do that in the context of this vast, ever increasing, exponentially expanding universe. So it's this very radical. So then all of a sudden, you have a theory where our world is just this tiny little patch, this tiny little bubble. I'm going to show a cartoon of that in a minute. Another thing you can do is say, oh, I hate that extrapolation. There's something really wrong with that extrapolation. And I was just talking with some of you right before the talk about interests I have about ideas that could cut off this extrapolation. So that's another. So you don't have to buy this extrapolation, but trying to cut it off is also a challenging project. And so for this talk, I want to emphasize what that extrapolation looks like. So this is a cartoon where you have the hash region is the eternally exponentially expanding region that comes out from that highly quantum fluctuating zone up at the top of the potential. And then little regions can fluctuate out of that behavior and start rolling classically down the potential. And you can have different regions in different spots, and maybe they have different features. Maybe there's different kinds of regions that look just like our universe, but have different predictions for future data we might take. And so what you really hope is that you can assign, to make predictions in such a situation, you want to assign probabilities. What's the probability that we're in one or the other of these different kinds of, we call them pocket universes, different little regions that are potentially looking like our cosmos that we see around us. So you want to ask, where are we in this big thing? You expect our theory to give probability distributions, but then you also face with this idea, as expressed by Alan Guth, one of the founders of all of this, that anything that can happen will happen infinitely many times, and then you can already see, touching base with this counting argument. So anything can happen infinitely many times. How can you tell what's more likely, which one is more likely than the other, and how can you assign probabilities if there's infinitely many of everything? It's sort of the way people get puzzled. And if you start thinking about the string theory landscape, all this gets even more complicated. So I found a cartoon of a monster. So eternal inflation can seem like a monster with all this stuff going on. Yes?
Okay, I'm confused. Are these different, these aren't different branches of the universe? These are different possible theories with different initial conditions, or are they different parameters or different rules?
So they can, so there's quantum fluctuation, so there is branching, but even on one branch, there's this giant multiverse with many pockets. So even classically, there's a lot of different regions separated by stuff that doesn't look anything like our universe. So there's little pockets that look like a Big Bang.
Is it in the space of theories?
Even in the space of just the space of metrics. So it's in the space. So in the space-time that Einstein's gravity tells you is there. So it's telling us that space-time is much more large and complicated.
Only one of those is realized in practice, or multiple ones could be realized?
No, the idea is that all of this is realized in practice. Even on one, if you think many worlds, even on one branch, all of this is, even one branch is this big Swiss cheese. Well, you know more about Swiss cheese than I do. Yes.
So the point is that one of these bubbles is our observable universe, and then you have, the idea is that there might be other regions of our space-time which are inflating differently,
Yes.
with different, in particular, different coupling constants, different,
Yeah.
because like, the inflation could have frozen in other ways.
Exactly.
It's like if you're in a magnet, or you have different parts that are
Different
settled
domains.
down,
The
Yeah.
probability,
different domain.
we're playing a role in this, basically. It's the probability that we're in a particular region.
Yes.
Okay, where that will realize.
We don't necessarily know where we are. So I like to give, as an example, suppose we have so we don't yet know the neutrino masses. We know some mass differences, but we don't know the neutrino masses. But suppose it could be quite possible that there's different kinds of pocket universes with different neutrino masses. So, and you'd really like to make a prediction, for theory X, which mass do you predict? People are going to measure these things. What is your prediction? And if there's different pockets with different neutrino masses, how do you make a prediction? How do you assign probabilities? It's another example.
So the occurrence of small pockets you attribute to the quantum fluctuations in the very early.
Yes. Yes.
I wanted to ask, what happens when two bubbles meet?
There's some nice work on that. You actually have to tune parameters there's the trend in sort of a typical setup would be they really don't meet, but people, there's some nice work on what if they meet and what would you see and all of that, yeah.
Also,
and we haven't seen it, so, yeah.
I probably haven't gotten everything, but why would neutrino masses be different in the different pockets?
Because of, yeah, so I've not really explained that, but these pockets could be forming through some kind of phase transition that goes one way or another. And for example, you could have a symmetry breaking field that breaks it one way or another. Or something. Yeah.
Can you remind me what's going on between the pockets?
So between the pockets, this inflaton field is up the potential, generating lots of exponential expansion and lots of quantum fluctuations. Definitely inhospitable to us. I like these questions, so keep them coming. Okay, so we've been going back to my slides, so we're back here, and this is called the self-reproduction regime bound by quantum fluctuations, and it leads to the multiverse. And now I'm going to set that aside. So here's this vast thing. So we're saying the universe is much, much bigger, infinitely bigger than what we see. And now I'm going to pause that and talk about a 2-qubit system.
So much happier now.
Yeah. I'm going to talk about a 2-qubit system, and I'm going to pose the problem that's present for multiverse in the context of the 2-qubit system. So here's a 2-qubit system. The universe is made out of qubit A and qubit B. There's a basis. I choose a basis for each of the qubits. Here's the basis for the universe with 4 basis states made out of the 2 bases for the qubits. And now you could say, so having said I'm fond of many worlds, I'm going to sort of put that aside and just say, for these purposes, so even though this whole thing of what is a measurement, you choose a Hermitian operator and you find the eigenstates and eigenvalues, blah, blah, blah. That's a pretty good sort of representation of what happens. So what I really think you should do is put the apparatus into the Hilbert space, and solve the Schrödinger equation, and watch the apparatus and the object interact and become entangled. But I'm not going to do all that for this. I'm going to say, so at the end of the day, all of that process is the idea that you choose a Hermitian operator representing the measurement is a good representation for what goes on. And I'm just going to use that way of thinking for what we do here. So in particular, you associate possible measurements with projection operators, projecting on eigenstates of the Hermitian operator that measure that represents your measurement. And so if you want to ask about measurements you can make, you have to construct sets of projection operators. So you can talk about making measurements just on A by looking at projection operators that just project on A and don't do anything. You can talk about measurements only on B, which do the equivalent thing, just focused on B. You can also measure the whole, any state in the whole universe if you can use this projection operator. But what if I say, I'm going to measure this, I'm going to measure a qubit, but I'm not going to tell you which one? What can you predict? And so suppose you have the whole wave function for this 2-qubit universe, and I say I'm going to measure a qubit, but I don't know which one. What can you predict for the outcome? And it turns out there's no projection operator that can represent something like that. And I think the only way to really understand that is to play with it. And I was on the verge of writing to Don Page when he wrote that paper and said, this can't be right, I just don't believe it. And I thought, okay, before I do that, let me check this for a 2-qubit system. And I worked it out and ended up not sending that email because I ended up agreeing with him. So if you do not know whether it's A or B that you're measuring, what could you do? Well, you could do something like this. You could say, well, the projection operator could be some mixture of projecting on A and projecting on B. Now, these would actually end up being classical probabilities. These are things you put in by hand. They're not something you extract from the wave function. And so doesn't look very quantum. And actually, this is not even a projection operator. It's not idempotent. It doesn't obey rules that projection operators have to obey. So it's actually not a good example. Now, Don Page said, okay, but to deal with the multiverse, you need to do something like this. So now this is a stand-in. So the essence is that you can't write a projection operator of this sort if you don't know which part of the Hilbert space you're going to measure. And in the multiverse, the idea is you don't know which part of the Hilbert space your pocket universe resides in. And so that's the real thing that's going on. And you don't have to have a whole massive Hilbert space of the multiverse. You can just pose that question in a 2-qubit system. And so Don Page barrels ahead and says, oh, but we've got to deal with multiverse, and so this is what we got to do. We've got to find values for PA and PB and build these kind of projectors, well, except they're not projectors, build these kind of operators. And so this is where I say, where do these things really come from? Don Page and his cohort would say, oh, they're classical probabilities, just like lots of things are classical probabilities. And this is where I say, hang on, all everyday probabilities are actually quantum. There's no such thing as classical probabilities. And our only experiences with practical applications of probabilities are actually with quantum probabilities. And so I'm claiming that even though we call them classical probabilities, they're really quantum probabilities, and we shouldn't just import those. We shouldn't think we have an extra tool at our disposal when it's really not extra. It's part of quantum physics, and I don't want to make there's too much clutter on it. So I'm jumping over it. But yeah, so I think I can just skip some of these details and say, yeah, so basically I said, now you can never stop a theorist from coming up with something new and building some new formalism and building it into their theory, but I personally was not excited to invent something brand new, classical probability theory, just to save the multiverse, which is pretty difficult theory anyway. So now I want to say why. So why do I think this about everyday probabilities? So I'm putting this aside, switching to everyday probabilities. Any questions? Yeah. Questions?
Sorry, I don't think I fully understood. I think I understood what are non-quantum probabilities.
Yes.
But what are quantum?
Good. That's what's coming next. That's what's coming next. That's the perfect question for next. But I saw another hand. Is there another question? Okay. Yeah. So when I finish this next section and you're not happy, you ask the question again. So I'm going to start by talking about a billiard gas. And I'm going to look at quantum effects of a billiard gas. So I'm going to take a billiard gas and I'm going to look at two billiards getting ready to collide. And I'm going to ask about quantum uncertainties in the impact parameter of one billiard aiming toward another. And I'm going to say, well, there's the uncertainty in the impact parameter is given by the uncertainty in the perpendicular x direction, and also the uncertainty in the momentum that grows, that impacts the position as time evolves. So there's an expression like that. there are several choices I make in this calculation that are intended to be conservative, so to minimize the effect. So I'm going to end up arguing this is a large effect, and I'm going to simplify the calculation by being conservative. And if I still get a large effect, then you shouldn't be worried about this simplification. So one simplification is to put the billiard in a minimum uncertainty wave packet. And when you do that, you get an expression of this width of the wave packet showing up in the picture. This is just the average speed of the billiards. The billiard path speed, v bar. And L, okay, I should tell you. So L is the mean separation of the billiards. V bar is the average speed, and A is the width of the wave packet. Now, in that result, you can it's still a minimum uncertainty wave packet, regardless of which value of A you choose. And I furthermore choose A to minimize the uncertainty in the impact curve. So you can dial A, it shows up here and there, and you can dial it so it balances terms to minimize the effect. And that ends up giving you this expression for the quantum uncertainty in the impact parameter given these conservative assumptions. And then those of you who think about ecoherence, there's a side point that might actually justify this in terms of physics, interactions with the environment, maybe. Now, subsequent collisions amplify this uncertainty, and again, I'm going to be conservative. I'm just going to take quantum uncertainty in the first collision, and then let it be amplified classically by subsequent collisions. That's obviously a very conservative assumption, because there'll be quantum uncertainty every step of the way. So after n collisions, I get this expression that it grows geometrically with each collision. And I can consider the question, how many collisions does the billiard have to experience before the uncertainty in the impact parameter is equal to the size of the billiard? So I don't even know what billiard I'm going to collide with next. So it's sort of a full quantum uncertainty in this behavior. And that's just easy enough to solve. So it's a simple enough expression, you just write down the answer. What is that number? Now I'm going to plug in some actual physical numbers into that expression. So what is the number of collisions before you go full quantum for different things? I'm going to start with something very classical, the bumper car, and I'm going to put in these are all MKS units, so radius of 1 meter, mean separation of 2. Mass of 150 kilograms, half a meter per second, average speed. You work this out, and it's after 20. So if you imagine a billiard gas with these properties inspired by the bumper car, after 25 collisions, you're fully quantum.
Wait, sorry, what do you mean by fully quantum?
So you don't know which billiard you're going to hit next because the quantum uncertainty has gotten so big. It's as big as the radius of the billiard. Yes?
Is this growth related to the fact that the system is chaotic?
Absolutely. Yeah, it's exactly what's happening. Yeah. I was always looking puzzled, so I wanted to give her a chance to. She doesn't look completely satisfied with my answer.
Wait, okay, so it's the 26th collision is one that you could not use your classical initial conditions to predict.
It's sort of full. I mean, it builds up over time, and by 25, you're totally lost.
The chaotic system, at some point, any uncertainty will be amplified to a macroscopic level.
Yeah. So, does someone want to guess what the number is for the billiard gas?
5.
Yeah, good. Say. So this means that if Elon Musk wants to spend his entire fortune building a robot to play billiards, he won't be able to control the outcome of collisions.
So here we're assuming they're in a fully isolated system, in complete vacuum, and there's no interaction.
Right, so in fact there's much more. So especially like you know, if you have little kids driving bumper cars, it's much more uncertain than the quantum uncertainty, right? Yeah. So this is sort of the minimal quantum uncertainty that lies underneath all the other crap.
No, but what I mean is like, you're not going to observe these quantum effects if you're entangled with the system, right? So you need to somehow completely isolate yourself from the system to start seeing interference effects.
Let me get back to that after like 3 or 4 more slides,
Okay.
and then stop me. When I'm talking about Brownian motion, stop me if you're still not happy. I'm about to go there. So water and air, it's less than 1. For air, it's less than 0. And basically the expression breaks down, but that's okay. It's just quantum at every collision. It's not about counting collisions anymore. It's quantum at every collision. And I have to say, I was surprised and disappointed to get this. I was disappointed that, I mean, the billiard gas is like this go-to model that everyone's supposed to think about when you learn about gases, right? And so I don't know who I was more disappointed in, me or my teachers, probably me, because any student, you can work this out. It's not like it's some hidden, mysterious, deep computation. This is just tiny little bit of arithmetic, a little bit of physics. And I'm curious, I always ask my audiences who knew this about billiard gases. And I've given this probably in front of probably a few thousand people, many seminars at this point. And only one person, so Larry Ford, Tufts, said, oh, I give this as a homework problem. But everyone else is surprised. I was totally surprised. I felt the pride. I don't think anyone should go through undergraduate physics without knowing this. It's interesting.
But then the question is, why does it work, the standard, like the statistical mechanics approach?
Well,
it's so wrong.
There's lots of randomness. It's not really about individual classical behavior. It's about ensemble. Mm-hmm. I'm basically arguing this is where the ensemble comes from. Mm-hmm. Yeah.
So I have 2 questions. Doesn't the Ehrenfest theorem tells you that on average, the system, as long as it's not chaotic, is going to follow the classical path? But also, where's the chaos in this billiard example?
So it's, for example, how the impact parameter grows. So it's some value with the first collision, but then it's amplified. The angle opens up because of the sphere, the way the spheres collide. It opens up for the next, and wider for the next. So it's this nth power that's compounding it step by step. Okay. Yeah.
I'm trying to understand what is the practical experiment I can do to distinguish this quantumness versus just the chaoticity of just the classical.
Because you're concerned about all the other effects that are impossible to factor to remove. I'm not going to try to answer that right now because I'm not sure it matters for what I'm doing, but keep me honest. So who here, oh yeah, go ahead.
I think it's a similar question. So what actually is the difference between it being quantum collisions only and us just not being able to predict it anymore to any reasonable accuracy? So is it interference then, based on the quantum uncertainty, or what makes it actually quantum rather than just uncertain in a way?
So, give me a couple more slides. I'll try to. So that, yeah.
I think really similar to my question. I'm still a bit confused by what it means to be like quantum after like NQ collisions. Does it mean like we can no longer use like classical mechanics to describe it, or?
So I'm gonna go to the next slide, which I think is gonna at least take us in the direction of these questions. which is, but I'm going to first ask the question, who here has witnessed examples of Brownian motion? You can look in the microscope and actually see Brownian motion. So some of you have, and these days you can just Google it and there's videos of it, so you don't have to. I remember in some science class in high school, having a microscope and watching Brownian motion. So here's a snapshot of the video I found on YouTube. And these are, I think, fat globules in milk, or what they jiggle around. And the claim is that every Brownian motion is a Schrodinger cat. So that these motions are drawn from a quantum ensemble. And the quantum state of the system represents many possible motions of each fat globule. And U seeing one is a quantum measurement of the selection of one of the many Schrodinger cats. So,
what do you mean by is a Schrodinger cat?
Sorry?
What do you mean by is a Schrodinger cat? You just
So
mean
it's a
multiverse.
superposition of different, so it's a quantum superposition. So where does this globule go next? The wave function says it could go here, it could go there, it could go there. And it's a quantum superposition of all those motions. Yeah.
So the claim is that the initial quantum uncertainty eventually dominates over the uncertainty due to coarse graining of the system. So you're saying that the Brownian motion,
it emerges from
that effect is dominated by.
in the end. Yeah, so everywhere you look, all the stuff you were saying, it's the other uncertainty, that's also dredged up from the quantum, and it's dominated by the quantum. So is that starting to answer your question? But how about the other people who are asking similar questions? How's that looking? Okay, keep asking as we go along. So I'm going to slip in a claim that these points are independent of interpretation. So there's Copenhagen, there's many worlds, something I Googled. I had to update my many worlds because the thing I was using was out of date. Used to be Facebook had a little globe for the messages. Anyway, it's a bad joke. Manuel will appreciate it. I'll show them the old slide. So it's not about interpretation. And this result is the root of our claim, my claim with Dan Phillips, that all everyday probabilities are quantum, because they emerge. The chaotic behavior all around us dredges up quantum uncertainty and brings it into the classical world. And it's absolutely nothing about quantum coherence, because there's endless decoherence going on along the way. But it's that all these uncertainties start out with orthogonal uncertainties from quantum effects. And I'm now going to give an example, a specific example, but stop me at any point.
Can I ask?
Yes.
So, for instance, in this case, for this Brownian motion, we can imagine that if we observe this Brownian motion, the system will collapse in some
Yes.
state. Let's say.
Yes.
So, if we don't observe, we have all this position of all possible paths. And in principle, we can imagine to have some experimental result or some observable, such a way we can measure the fact that we measure the system, we observe the system, and we obtain a different result.
I'm gonna, I don't have a snap illustration of that sort for you, because I think I'm not, maybe the point is I'm not predicting anything new for Brownian motion. We observe the study, but I'm talking about where the uncertainty comes from. Yeah.
So you're saying that basically the only real randomness stems from quantum randomness.
Yes.
But there's still, of course, a notion of classical probability that I can just talk about my ignorance of things, right? If I flip
So I can get to
keep them in my hand, there's no intrinsic randomness. But
so I'm going to build toward that slowly, a little more slowly. So I'm going to give an example about the coin flip. So I'm going to work out how 50-50 the coin flip can be traced to quantum. And to do that, I asked my then student Dan Phillips how are we going to learn some neuroscience? He said, oh, I have a friend who's a neuroscience graduate student. And he went and talked to his friend and dug up the Nature paper. And it turns out that, so every neuron has a transmission time. So you stimulate one end, and a signal comes to the other in a certain amount of time. And there's the transmission time, and then there's the uncertainty, the unreproducibility of that transmission time. So there's an uncertainty around the millisecond that is understood by the experts in this way. So neurons have proteins called polypeptides floating around in the cellular fluid, whatever it's called. So I'm really at the limits of my biology here. There's ion channels, and the polypeptides can show up in the block the ion channels. And the fraction of ion channels that are blocked controls the transmission time of the neuron. And in fact, neurons can change the density of polypeptides, and by that control their response time. So in a crisis, you want faster response, and I don't even know the sign of this effect, which way it goes. It either increases or decreases in the percentage of polypeptides, fraction of polypeptides in the neuron, and gets the desired result. But at the end of the day, you can have a certain density of polypeptides, but how many actual ion channels are blocked by the polypeptides? What, 10 minutes? Or how many ion channels are actually blocked by the polypeptides is given by Brownian motion. So of all the polypeptides, how many have actually showed up in the ion channels? That's Brownian motion. And so I'm claiming, because I claim Brownian motion is quantum, I'm claiming this uncertainty in the transmission time is also is a quantum effect. So I'm saying these are, when you stimulate a neuron and make a high precision measurement of the transmission time, the actual value of the transmission time has uncertainty that's drawn from a quantum ensemble. Just re-emphasizing that with the slide here. And then we work out, and that's, I'm not going to slog through the details, but we then work out the coin flip, where everything's classical except the process of when you do this, but when you think flip, when do you actually flip? There's that millisecond uncertainty, and that's enough to give you 50-50 uncertainty of the coin flip. So I'm claiming 50-50 of the coin flip is a derivable quantum result. Now, and without, so I have a real bee in my bonnet about the principle of indifference, which says that if you have a bit and you know nothing about it, there's some mathematically virtuous point of view that says you should choose 50-50 probability without any physical input. I claim principle of indifference is unfounded altogether. Certainly in this case, it's quantum derivable, not 50-50. Now, so the word on the street is that there are some people who can control their coin flips, and certainly a robot can. And if you dig through this calculation, it is at the margin. So if you dial, so there's various free parameters, and you dial them one way or another, you can get it below 50-50. So on. So I feel that in a way is validated. It's a technical question, how much of these fluctuations are amplified in a coin flip, and you can dial it to be not 50-50 or be 50-50. So I think it's a good illustration of including being at the margin. It's a good illustration of all of these points. Now I want to make one more point, which is, so here's Bayes' theorem. And the probabilities I'm talking about are really driving the randomness in this part, which is the probability of the data given the theory. So if you have a theory, I'm saying uncertainty in your data really comes from quantum uncertainty. So you can say it's noise in the detector, you can say it's thermal, this or that, all these things. But I'm saying all of those things are going to have the property of the Brownian motion or something similar, the chaotic amplification of the quantum uncertainties. Now, there's also the prior that you have, and the prior is actually mixed in. So you can today's prior might be influenced by yesterday's data, and there's sort of a tower of influence. But at the end of the day, there's sort of a prior, an initial prior that's unpolluted by data, and that's sort of your beliefs. And I'm claiming what I'm talking about is not that probability, but only these probabilities that show up in your data as opposed to in your beliefs. And then you can ask, well, what is the role of the prior? So we can get into all that, but I'm counting my minutes, and I'm saying that these probabilities are the only place where physical randomness appears. Now, how do we make? So I've just given one example. How do we make the case that this is always true? Well, we can't do proof by exhaustion. I'm already pretty tired just doing this. But one counterexample. So one example of where practical randomness clearly comes from non-quantum sources would really undermine all of this. And this has been out for several years now, and people still haven't done it. You can still invent classical probabilities as a concept, and use them as there's like to invent things. Skip some further, yeah. So there's lots of sort of fine-grained implications I'm going to skip through for the purposes of wrapping up this talk, but I want to, here's a point. So you actually need quantum physics to understand color, but that hasn't stopped great artists. These guys didn't know anything about quantum physics. It didn't stop them from doing great things with color. And I'm not saying hold everything, stop using probability. We're creatures that work with probabilities all the time, just to manage our everyday lives. And I'm not saying you're doing it wrong. And so we do make mistakes, but I'm not questioning that. Just like I'm not saying, hey, you artists, stop doing what you're doing until I teach you quantum mechanics. That's not what I'm doing. But I'm saying, if you're going to do cosmology, so this is a sort of niche topic, if you're going to do cosmology and you're going to consider a case where there are clearly no quantum probabilities, and you're going to import the idea of a classical probability, I'm claiming you're importing something brand new. You can't rely on you can't say it's classical probability as we know it, because it's not. It's something new. You're just inventing. That's my claim. Now, my favorite counterexample that people thought of is, what about betting on the digits of pi? Like, that sounds completely classical. It sounds like a random thing, but it sounds completely classical as well. Like, if I say, let's bet on the millionth digit of pi, and we place our bets, and then we look it up. So, if you think about that, the only reason that could be a possibly fair bet is if we don't know the millionth digit of pi. And furthermore, if neither of us know, then really what we have to do is choose which digit we bet on in a way that's uncorrelated with its value. And so whether I say millionth or billionth, I would claim is coming from my neurons. And I'm not in the minutes left, I'm not going to hack through this, but I've had plenty of fun conversations about this. This is actually fundamentally quantum in the way that matters, even though pi is perfectly flexible. You could say, what if we model all this stuff, model a coin flip, model a neuron on a classical computer? And then we could ask, or we could just ask, where do random numbers on a computer come from, which you would use to set up this model. And random numbers on a computer, on a classical computer, are totally classical, but they typically look for a seed from the timestamp or something. And that comes from when you press enter. There's your neurons in there. So we can, I'm offering these subjects as debate. We're not going to hash it out all here. In like 2 minutes, I can have 2 minutes. Right? So I'm going to just talk about being careful about counting. Here's an example. We can flip a coin and fill a bowl with red or green balls, depending on outcome. And the counting of the red and green balls are related in very concrete terms to the probability of heads versus tails. And then I can ask, what is the probability that the ball drawn from the results bowl is red? And you'd be tempted to use those same counting arguments to draw the bowl, but actually, I haven't told you enough to know. The green balls could have sunk to the bottom. I could have had some compulsive behavior and set the balls up like this. So ultimately, you need, I would say, probabilities are physical things, and you need to physicalize the answer. Until you include enough physics, you can't give an answer. Counting arguments aren't enough until you give an answer. And who here has heard of the Sleeping Beauty problem? A couple people. So I will claim the Sleeping Beauty problem is fundamentally a problem where you feel not enough physical information is given, but you feel obliged to use the principle of indifference as an abstract thing, and you're not, you don't have enough information to know. There's not enough information to say what the principle of indifference means, because it's meaningless without physics to back it up. And so it's just another example where it's not physicalized enough. In the multiverse, the claim is you don't know the physicalization, and so you've blocked out, you don't know what's going on. And that's where, at least apparently, there's another question of whether people have really thought about the multiverse correctly. And it could be, for example, so we had a conversation earlier on about what makes the different pocket universes, and maybe it's the inflaton rolling in different directions. Maybe it's actually tunneling in different directions. Maybe there's a quantum branching ratio in the different directions, and then we'd be fine, and we wouldn't be counting. We wouldn't care that there were infinitely many pocket universes. We'd have a quantum probability to assign to the different universes, and then we'd be fine. I want to make, what happened to that slide? Anyway, one more point, and then I'll do my last slide. So if you, back to quantum interpretations, what if you ask, what about the poor guy who flips a fair coin and gets 1 million heads? And isn't that, so this comes up for the many worlds, like what do you make, that guy's real, what do you make of it? Shouldn't he be counted equally to all the other branches? And then that's the counting argument again. I say, no, you need to assign that guy the Bornville probability for that, which is tiny. And we ignore low probability things all the time. So that's just a sort of provocation. So I think this subject comes into those kinds of conversations about interpretations. This is all cosmology stuff. I want to skip to my very last slide, which is just to say, one of the things I love about this topic is we just tie together all these different things: cosmology, billiard gas, coin flips, Brownian motion, digits of pi. And I just want to thank you, and hopefully there's more questions. And we'll see what you think, see what you make of all this. Thank you.
So if we think about the coin flip again, usually we use probabilities because we don't know initial conditions. And there we say, okay, classical probabilities are already not physical because it's just ignorance. But you say even if we knew the initial condition, it would still be
Yeah.
random.
Yeah. And then further, I claim that all
So I
the
think
all
I
the
know
initial
what you
conditions we
meant.
don't know have dredged up quantum uncertainty in their
That's right.
formation.
So I think I understand what you meant by classical probabilities since the beginning. You say they don't exist, but what are they? Because
They're
every time we
swamps.
use them, it's because we don't know something.
So one of my favorite conversations about this came, so after we put the preprint out, I sent it to a couple of colleagues to get their reactions. And Tom Kibble from Imperial College came back and said, so what about generating random numbers from the positions of galaxies? And which sounds good until you think that the popular belief now is that those positions actually came from quantum fluctuations from inflation. So it seems like there's some kind of quantum. What's the word in physics in gravity where black holes protect their singularities with horizons? There's some cosmic censorship. So there's quantum censorship as well, that no randomness gets to us without being from quantum. So you could imagine, so in the classical Big Bang without inflation, you could imagine the positions of the galaxies emerging from initial singularity is a classical thing, and that could be a source of randomness. But it's not in the current theory, yeah.
So you mentioned in the beginning that you think it has some link with the quantum measurement problem.
Yes.
Maybe you can quickly.
Yeah, I flew past that. So the way it arrives is people who worry about the rare branches of the many worlds, like the guy who flips the million heads, say why should I ignore the guy who flips a million heads? Because aren't all branches equal? And I'm saying no, not the bottom line is the Born rule probability. All branches are not equal, and I'd say we know we believe that. So I decided to take this trip. It's possible I would have died in a plane crash coming here, but I did the probabilities and decided it was okay to take the trip. If planes were crashing all the time, I would have reconsidered. That's me ignoring. That's the same thing as ignoring the guy who gets a million heads. It's low probability, and so it's too late. So if you really care about the guy who gets a million heads, you shouldn't take planes. You shouldn't take any risk because all of these low probability outcomes are equal in some way. So that's the way this topic has entered into my conversations about. So there's people who think there's something wrong with many worlds because of all the worlds with unlikely stuff on them. And I'm saying we're already used to ignoring those worlds because those are getting probabilities assigned by the Born rule, just like the probability of my plane crash is. Quantum measurement conversations pull people in many different ways. So I don't know how compelling you find that, but I find myself turning to this when I get in those arguments.
Okay, could maybe do one more question?
Maybe I can just rephrase the question from before. But so I think that nobody believes that there are intrinsic classical probabilities in nature, right? Because we think that
except for Don Page.
But if you I think you also would agree that if you knew all the degrees of freedom of a system, like at Maxwell's demon, knowing everything classical, but in a classical theory, you could predict the future and the past deterministically. And the only intrinsic randomness is quantum. So is that,
So when I mentioned at the beginning that people think it's trivial, so there's something trivial that say, well, the world is quantum. I would say that the trivial account is the world is quantum and that it's full of chaotic processes like Brownian motion, which dredge up the quantum probabilities into everything. And in that sense, it is pretty trivial. And I'm not telling you to go and do probabilities differently. I'm just telling Don Page, be careful what he says about classical. Don Page and Jim Cardle and those guys, to be careful and again, they can invent classical probabilities. But I would say it's a new thing, and that what we've been calling classical probabilities so far are really fun. And so it's not, right, so keep painting beautiful paintings. Don't worry about quantum physics, but in the esoteric world of the multiverse, that's the only place where I'm really trying to make trouble with this. But then it turns into fun. Like at least hopefully you didn't feel you wasted your hour here. And so I'm not asking you to change how you work with probabilities, but it's been fun for me to just yeah. And it's an interesting topic. Curious.
Cool. Then I think we're probably going to kick out of the room soon. So let's thank Andy again. Couple of quick announcements. One, if anyone wants to sign up for the